Hello, everybody. Welcome to the next webinar that we're doing. This is the fourth one. My name is Tom Danvers from Waygate Technologies. This is the webinar on 3D stitching using Real3D measurement images and data. And we're also going to take you through a new topic, a new area upon which we've invested quite heavily into in terms of bringing advanced algorithms into our boroscopes. And we've kind of turned those as analytics. So the second half of this session will be talking about analytics. So following the same format as the previous sort of webinars that I've been running recently, this is really looking over what I'm aiming to do and to provide you an insight onto really more about giving you awareness about stitching and also the analytics and how that really helps you in performing your inspections on the asset, and also enabling you to capture more information, report more information, share more information, and also from an analytics point of view, how really those analytics fit into your existing workflows. So 3D stitching and analytics is what we're going to be taking you through today. Brief overview again, you've heard me say this in previous sessions, but it can be considered a complex topic in terms of measurement types and the different technologies that we have within our products. We have 4 different types: comparison, stereo, and also 3D stereo and 3D phase. We've grouped 3D stereo and 3D phase some years ago and called that Real 3D measurement. So 3D stitching that I'll be talking to you today concerns Real 3D measurement, which essentially is 3D stereo and 3D phase. Those are the vast array of measurement types that are concerned with that technology, with Real 3D measurement technology. But with regard to stitching, there's a subset of those measurement types. Not all of those measurement types are compatible currently with 3D stitching. So you'll see the measurement types that I've now shown in bold on this slide: length, point to line, multi-segment, area depth, and radius gauge. Those are the ones that our measurement types are compatible today with 3D stitching, whether you're using a 3D stereo tip or a 3D phase measurement tip. So a little bit more now about 3D stitching specifically. So what is it? Enabling you to, in this case, this is a video taking you through the stitching of 5 previously saved 3D phase measurement images. So I'm calling this option 1. This is how you can stitch images from recalled videos. So you've seen at the beginning of this video, I've gone into my file manager, selected 5 images that were previously captured on the inspection. And if you've done that, you've gone off and completed the job, and you might choose to then stitch those images together. And so I've stitched them together. And yes, I've clipped like about a minute. It could have been actually a minute, 10 seconds. There's a lot of processing time to stitch these images together. And for really, that is the main reason why there's a maximum limit of 5 images that you can stitch together. And once it's stitched together, you're able to interact with that full, sometimes call it composite image, the full stitched image. And then you can treat it like any other Real 3D measurement image. And essentially, in this case, you'll see me applying a multi-segment length measurement to that stitched image. And yeah, this is an example where I've gone into a combustion chamber, and you saw previously earlier on in the video clip where you can show the tip model. And those are an accurate representation of where the tip or the probe was positioned when each of the images were captured. So you saw 5 differently oriented tips to correspond to the 5 different images that were used to create this stitched composite image. And then you can see here, when you've gone and selected into views and gone into the full point cloud view, you can carry out your measurement across all of those different images and treat them essentially as one image. So that's a quick overview of, of stitching on a recalled image. The next one, this is taken from a live video and intentionally from a real 3D stereo tip. So you've got a stereo tip as opposed to a 3D phase measurement tip. And just like you would today in terms of capturing a stereo measurement, you tap the screen and enter into the freeze frame state. The difference here when you're stitching is that you can capture that image, move your probe, tap the screen and enter into freeze frame again, and add these images to the stitch composite. So as you see me moving the probe and incrementally adding images to the previous images, you're able to generate the composite. So again, I've dropped into a combustion chamber and I've found quite a large defect that again requires more stitching in order to be able to generate a good quality image or measurement on the one single image. And just to reiterate, this is all completely possible with obviously 3D phase measurement as well as 3D stereo. So in this case, you see me, I'm in the stitching state. You can see on the top, on the status bar on the top left-hand side, when you enter the stitching state, you can check the quality of the point cloud that you've generated for that additional image that you've created and how well that is stitched or registered to the other images before then choosing to add that to the composite. Or you might choose to capture a new image as opposed to, you know, including that previous image into the stitch. So here, as you see me incrementally moving across the scene and adding images to generate the composite image, you get to see the composite screen. Another reason why stitching is so useful is to really understand not just the sizing large defects, but also zoning or locating the defects. So here I've stitched 3 images, not 5. So this is 3 images to form this complete image of a turbine blade. And with reference to the AMM or the aircraft maintenance manual, I've been able to determine the location of the different zones of this particular image. And that helps me convey well, not just to myself when it comes to sentencing a defect, but to the reader or the asset owner as to where these defects reside on the component. In this case, there's 3 zones on this turbine blade to correspond to the image that you see on the right-hand side. So yeah, using stitching to also not just measure large defects, but to also locate or zone defects is a very real use case for 3D stitching. When you are stitching, it's very important to make sure that you've got good quality images, because ultimately you're either wanting to present a stitched image within your reports, or potentially, or more importantly, perhaps to perform measurements on that stitched image. So to generate good quality measurements, you need to make sure you've got a good quality stitch. So using the feature that you see here on this video clip, once you've generated your individual images and stitched them together, you can interact with the point cloud and determine how well visually they've stitched together and matched together. It is sometimes possible that, you know, registration or stitching hasn't performed so well, in which case you can delete that image or not include that image in the composite, and you can continue capturing more. So you can capture many more than 5 images, but you can only actually stitch 5 images as a maximum together. So if you choose to discard some of the images that you captured, that's fine, in order to reposition the probe or reposition the component in relation to the probe, and stitch again and reattempt the stitch in order to make sure that you've got a good quality match between all of the individual images together. And that enables you then to proceed to the next step, where you've got your, you move away from the stitching state and enter into the measurement state. Once you're in that state, you're now dealing with one single stitched image rather than 5 individual ones. So checking the quality of your stitching is very important. So I put the list of some best practices together, really to help you understand how best to extract 3D stitching and use it to your best ability on your inspection workflows. So similarly to all measurement types, it's very important that you consider tip to target distance in relation to your probe and your component, your target component, how far away you are to each other. Now that distance can vary depending on what tip you've got fitted. So having good understanding of which tip you've got fitted and working well within the physical parameters of that tip, making sure you're, generally speaking, as close as you possibly can be in order to get very clean quality real 3D measurement data out of that image. And stitching works with registering visual features in the visible spectrum before they're sort of connected to the point cloud. So having clear features on individual images that overlap each other significantly, as you see here, at least half or 60% of overlap, but having a rich content of features visually on the scene really does help to get good quality stitching happening. And target material composition. So it's a little bit similar to Real3D today, in as much that there can be instances where you've got highly reflective or shiny surfaces, certainly in booster sections, in gas turbine inspections, for instance, or at the front of compressors, where they don't get really hot enough to oxidize significantly. So they always are very shiny and can be reflective as a result. Those are examples where it can be very difficult to get a successful stitch happening, or indeed if components are wet or oily, same again applies. So those could be instances where you can't really actually successfully stitch at all. Worst case situation. But managing that can be a challenge, because obviously you can't really interact with the component in most instances to make that better. Yeah, stitching must happen on the same probe, but also the same tip that you've got. You can't mix and match images from different probes or different images captured from different tips. So it must all be, they must all basically assign to each other. And the calibration that you have from each of the tips aligns with the other images in that composite image. And as you move from each sort of position or pose of the probe across the scene, you really need to avoid significant rotation and also magnification, moving in and out, for instance, and getting closer or further away from the component. So there is some degree of tolerance. Actually, you saw earlier in one of my first examples where I was showing you the tip model of the position of the tips in the combustion chamber. There was those tips. Those tip models were in a space that was very different to each other. So there is good degree of tolerance, but if you exceed that tolerance, then you'll encounter areas where successful registration will not happen. So you need to limit that. So yeah, just be aware of that. And like I've said in my bottom point there at the bottom of the chart, just checking, making sure within this stitching state before you move into the measurement state, flicking through the different individual images, interacting with your point cloud, checking that you've got good registration, good matching before you then proceed into the measurement state and start working through and analyzing that scene with the stitched image. So that's a quick run through of 3D stitching. This is a feature that we released last year on our MViQ. It is only available on the MViQ, not the Mentor Flex. But yes, it will work on, and it's available. It has been included in the top tier model which we call the Analyze model on the MViQ. And that will be a model, obviously, that has been activated with a real 3D measurement, whether it's 3D stereo or 3D phase measurement or both. If you have a device that isn't the Analyze model, but is activated with those, either the one or more of those two different types of measurement, then 3D stitching will also be included. and accessible to you over the air. So you need to make sure you're up to date with your software updates. This came out last year under 3.60, just like February last year. We're now up to 3.71 is the latest one. When this is recorded in November 2023, so we've moved on somewhat since then. But yeah, the time taken, we continue to optimize the process upon which we do 3D stitching. So it's getting quicker and quicker and more reliable, and the amount of required overlap between the two given images is reducing. So it's getting more and more robust in that capacity. So moving on from 3D stitching, analytics. Again, quite a new feature that we have now on our MViQ. Again, this is only available in the MViQ. Analytics is essentially a new button that you might see on the global menu of your MViQ. And if you've recently updated your MViQ, you would have had sort of a free 90-day trial to these analytics. What are analytics? Really, these are advanced algorithms that really help you do your job. You do your visual inspection. What they really are is we've got two different types of analytics. We've got a blade counter, and we also have analytics that are designed to help you detect defects. We call that assisted defect recognition, ADR. So both blade counter and ADR are now available on the MViQ. You find them within the analytics page that you get through the global menu button. And there's a lot of information about these analytics contained within these documents that we call data sheets. So I'll mention data sheets again later on in this webinar. But there's a few examples of what these data sheets look like on the right-hand side. So there's lots of information associated with how to operate them, what they're designed to do, and take you through situations upon which how to use them best, how they're not designed, how accurate they can be, what information they're based on. There's a lot of information contained within these data sheets. So those are very useful resources for you to interact with and obtain. So more detail. Blade counter. Yes, it counts blades, essentially. To set up and operate blade counter, for this video, I've kind of skipped the first 3 steps that you see on this chart. I've already loaded a setup and entered the total number of blades in this set. And as you can see on the video, that I'm actually counting blades as you see the LP turbines rotate in the scene. And I've then moved, there's an example where there's obviously multiple blades in the scene, so you're not quite sure which blade corresponds to the label or the annotation box that says blade 15 in this case. So I've moved it across to where actually the count takes place. We call that the trigger point. So we want that annotation box. I personally like to move that box to close to where that trigger point is. So if I chose to stop the blades and save the image and perform some measurement on some defect, perhaps, I know that the count on that box is appropriate for that blade that I'm interacting with straight away. So that's a quick sort of introduction to. There's more we'll talk through. But yeah, using blade counter, I mean, it can take, I think from memory, it took me, there's 9 interactions with the touchscreen, pressing buttons and manually updating an annotation box by sort of moving it from blade 1 to blade 2. You have to tap to edit, you have to enter into the text state, you have to press backspace and delete number 1 and enter number 2, then you have to press done 3 times. And that takes quite some time to do. So using blade counter, once it takes approximately 90 seconds, a minute and a half to set it up and go through steps 1, 2, 3, 4. But once it's on and running, it's a very efficient way of essentially labeling and counting. So when you're saving an image, it's a very efficient way of obviously capturing the blade number. In this case, if you're carrying out inspection where perhaps you're tracking defects associated with certain blade numbers in previous inspections, then you can use that. or if indeed you do it just doing a simple inspection, but you want to make sure that you're not inspecting, well, you're inspecting the full set, not inspecting less or perhaps more than what you need to do. So it's a very efficient way of making sure, assuming you know the number of blades that's in your set, that's not known by the instrument, it needs to be entered by you, the operator. Assuming you have that information, you're able to basically count very reliably as that inspection is taking place. So this is a blade counter that's trained on both the turbine and compressor stages. So here's another shot, in this case on the HB compressor, quite an acute view of the compressor blades. And you can tell by the rotation probably that it's quite a jerky, irregular movement. So because it's either me or perhaps one of my colleagues that's rotating the HP on this CFM 56. And it's a very jerky gear train, shall we say, and the ratio upon which you're turning the HP to the blades that you see in the gas stream is such that it's very difficult to rotate it in a slow, controlled space. But using blade counter, it's been designed to basically pick up the features, and as the scene passes, the region of interest passes through the trigger point that you heard me talking about earlier, it reliably triggers, and even though the blades are moving in both fast and very slow speeds, it's reliably picking up that edge as it passes through the trigger point, and it's counting. I hadn't said it earlier, but it counts up as well as down. So if you chose to sort of rotate and stop and go back, that's perfectly fine. It'll count up as well as counting down. One Achilles heel for this version of the blade counter is that the probe does need to be stationary. Once you've set it up and drawn these lines that I'm going to talk to you about now, you must basically keep the probe still. So you need to have that probe in a position where you're happy to do the inspection once you've set up blade counter. So this next slide really sort of focuses on how to set up the blade counter. So you're invited to basically follow the instructions on the blue text on the top of the screen. So I've placed the blue line, which was the entry line, and then I've rotated the blade and spun it to a point where I've placed an exit line. I'm just going to pause if I can. Pause it, yeah. So I've set up a blue line and a red line, which is the entry line and the exit line. So as the edge of the blade passes through those two lines, the edge is going to count. So the counter is going to be triggered by the central green cursor that you see on the limit line. The limit line is the yellow line that you see on here. So as that edge passes through the limit line, the trigger point, you'll see the count move. So that's taken me literally a few tens of seconds to place those three lines. I'll just roll the video on. Now you're invited to rotate the blade at least 3 times, and this is what we call the verification process. So you need to make sure that the blade counter is working with how you set it up. So we call that verification. So the last thing you want to do is invest in using blade counter and then realize it's not working or it's miscounting, for instance. So verification gives you confidence that it's going to work if it passes the three blade verification. It could be more blades. Sometimes I spin 4, 5, 6. It doesn't really matter, but a minimum of 3 is certainly the recommendation. So if it has successfully triggered for the number of blades that you've passed through the verification process, it'll say, did you rotate 3 blades? And then you answer yes or no. If you say no, then you're invited to basically move the probe to another position or change the lighting setup, or just try again, perhaps with different position of your lines, and basically go through the setup procedure. If it did count correctly during verification, which it did in this video, then you press yes, and then you're into this state where you basically you can start counting. You're now in the live state, and you can see me. I've moved the text box to an appropriate point to coincide with the trigger point, and you start your inspection. So generally speaking, that kind of takes a minute or a minute and a half to set up and start your inspection with blade counter. The label for the blade counter is the same as it is essentially for the manual annotation. You're able to interact with it and move it around. But as soon as you tap onto the blade counter overlay, basically the blade counter pauses. And there is a warning that appears on screen to say, look, blade counter's now paused. Just be aware that if you continue your inspection, it doesn't say all this, by the way, but if you were to continue your inspection, it will not count. So the idea is that once you've tapped on that label and you're moving it around, you need to press done and come away from that state and go back into the live state so that the blade counter is reactivated such that when you start rotating again, the counter is going to work. So it works, yeah, as I was demonstrating in the previous shots. So this is in the LP turbine again. So just slow manual rotation of, I guess, what would have been the fan, but also jerky rotation when you're sort of manually rotating or ratcheting the HP, for instance. So it works in all sorts of different speeds, lots of different scenes within the compressor and turbine stages. In addition to the blade counter that you've just seen, there is a dedicated settings page in the MViQ. So if, for instance, I'm just going to pause it here, go back, there we go. So there's a setting for current blade. So if you find yourself in the middle of inspection and I don't know, you might be at blade 32, for instance, and you now have decided, actually, I'm going to call this blade 1 because this is the defect that I want to track, and perhaps it was called blade 1 in previous inspections, for instance. You can go into settings and change the blade number that it currently is to whichever number you choose to put it, for instance, without stopping and starting blade count or anything like that. You can just go into settings and change the current blade count. The other, oh, I didn't mean to do that. The other setting, let's go back. The other setting is if you made a mistake with entering the appropriate number of total blades within the stage that you're inspecting. So when you've gone through the setup and the verification, you're doing your inspection and you entered, for instance, 76 blades, you realize actually there's more or less, the number's different. You can go into settings, change the number of blades in there. And I'm just going to let it roll on. Then there's another setting. So if you're performing an inspection and you're counting up, and actually what you want to be doing is counting down or vice versa, while still rotating in the same direction. Basically, there's this drop-down menu that you see here on the third line. So counting direction, you can change it from ascend to descend or vice versa, whilst rotating in the same direction. And sensitivity mode, that's something I've not talked about really, but again, there's lots more in the data sheet. But sensitivity mode is essentially a way upon which to, if there are certain scenes where it's difficult to successfully carry out the verification process where you're counting the 3 blades before you start your inspection, you could enter into this state, what we call the high sensitivity mode, where it's going to be picking up greater contrast between the edges as it passes through the region of interest and those lines that you set up. That's something that isn't really that normal, but there have been instances where we've needed to go to a higher sensitivity threshold. So that's a feature that helps you successfully pass through the verification procedure if you need to. So that's the sensitivity mode. So that's blade counter. Moving on to the other types of analytics that we have on our boroscope. So these are, as I was saying, assisted defect recognition analytics. Why do we have these? Essentially, we ran a research project probably 5 years ago now and realized that we had the ability to optimize these very complex, powerful algorithms to operate on the boroscope, on the MViQ. And we had access to thousands and thousands of images or boroscope inspection reports that contain defects. And so we with the algorithm that we developed and all of the data that we had access to, we developed algorithms that were trained to detect and categorize defects. And we launched gas power assist. We, being Waygate Technologies, released, it was called LM2500 assist about a year or so ago, but we've expanded the data that is contained within that algorithm. So we've kind of renamed it because it's more generic now, because it contains data from lots of other engine types, to gas power assist. And so that contains up to over 8,000 images that contain defects, and they're all labeled, and so those not just contain defects, but we understand the categorization or the classification of each of those defects. So it is an analytic that works in the live and the still state. So whilst you're doing your normal inspection under the live state, perhaps whilst also using blade counter, you can also be having this analytic running in the background, and I'll show you what it looks like shortly. It's designed to really help you carry out your inspection. It's not going to force you into anything. Once it finds something, you can either accept it, reject it, and not include it in the image that you're about to save. The idea is really it's there to help you make sure that you're going to be detecting all the defects that emerge into your scene during your inspection. The other type of analytic that we have here is we partnered with a business, a company called Air Innovations, that are based out of Amsterdam in the Netherlands. Now, Air Innovations specialize in creating artificial intelligence algorithms for the aviation marketplace. And our relationship with Air Innovations has enabled us to access their analytics on board our borescope, the MViQ. The Air Innovation products are called Air Edge Hot and Air Edge Cold. The hot corresponds to the HP turbine and combustion stages, as you might imagine, and the cold analytic, the Air Edge Cold, corresponds to components within the compressor and LP turbine stages. So these are analytics similar to what you've just heard me talk about with gas power assist. These are analytics that are trained through using artificial intelligence with many, many images, thousands of images, in this case, purely based on images from the aviation marketplace. So there's lots of data, lots of information in our data sheets in terms of all the different types of engines and the images from all the different types of engines that went in to feed into this analytic. So here's a video of gas power assist working. Yeah, it's just running. Okay. So I'm back in the compressor stage here, HP4 stage on a CFM 56. What you see, yeah, you can tell it's manual rotation again. So as there's obviously, in this case, there's gross defects emerging into the scene. Sometimes there are subtle defects like tip curl that you see here. So in the settings menu, I've turned on the indication box, the defect classification box, and the confidence box. That's why you see a blue box with some text around it as well. If those settings were turned off, all you would see is a yellow box around the edge of your screen, which you can see here to tell you that the analytic has found a defect. So it's depending on how you want to operate your borescope with this analytic, whether you have those that blue box and the information turned on or not. But the yellow box will always appear and disappear depending on whether it detects features or not. So this is, yeah, it works in the live state. This video doesn't show you what happens in the still state, but if I went into the still state now, having found a defect, the blue box appears in front of you around the defect, and you're invited to either accept or reject that bounding box. And a little green tick or a red cross appears next to that bounding box if you've accepted and rejected it. If you don't do anything with it, a little question mark appears there, so it will always be there before you save the image. So let's say you've rejected some bounding boxes but accepted others, and you save the image. All that data is always stored within the image, but when you come to recall that image, only the accepted bounding boxes or indications appear visible on the screen. The ones that were rejected are still contained within the file, but not shown when you recall the image. And as you can see, those are the 8 different defect classifications that this analytic has been trained on. Lots of different types. yeah, and designed for the whole engine type, the whole engines. That's why you see lots of things like dents and nicks, but as well as TBC loss and oxidation. So it corresponds to the turbine as well as the compressor stages. The analytics that we have from Air Innovation. So this is it going to play? Yeah, okay. This is an analytic. So this will be air edge hot. As you can see on the top right-hand side, we always have these info boxes displayed on the screen. It's important for you and your customers and anyone that sees either video images or still images from your borescope, that they understand which analytic was operating at the time. So here I've dropped into the combustion chamber and I've just clipped this part of the video just to highlight an area where it found a crack. And I actually did this, I actually captured this, and I remember not immediately seeing the crack, even though it's a significant crack, because my borescope was positioned elsewhere. But suddenly all these blue boxes appeared off the edge of the screen before I personally recognized that there was a crack there, and then moved the borescope up to that area, and lo and behold, you can obviously see a significant defect there. But it's yeah, that's an analytic, again, trained purely on aviation sort of hardware. So moving really to the summary now, we're moving to the end of the webinar. Just priming you now, we've got time for questions at the end of this. So if you can think of any questions, I'll be spending some more time answering any questions that you have on the end of this. So I've taken you through just a quick run through of 3D stitching and analytics. Those are the different types of measurements that apply to 3D stitching. Not all of them, but a significant number of them. Hopefully that list will be growing as we move forward. It's important to recognize that we have a maximum on today's MViQ, a maximum of 5 images that you can stitch together. But you can use 3D stereo and also 3D phase measurement tips. Important to, yeah, it's an important feature. It lets you really get close to a target, get a really good measurement image, but then move your probe to another position so you can create another image and another image. If you need more than 2, then off you go all the way up to 5 if you need to. So a very powerful way of getting really good quality measurements, because you're very close to your target, and you can move your probe across the scene and capture the stitched image all in one go. And for analytics, so we have blade counter and assisted defect recognition analytics. Yeah, main reason why we have these analytics is so that you can really focus on what you're paid to do, to carry out your visual inspection. Counting blades is a necessary evil. And now allowing the instrument to count those blades for you really allows you to focus on what you're paid to do, and to focus on the inspection and check for the serviceability of the asset that you're inspecting. And assisted defect recognition, it really does provide you with those extra set of eyes. If it's not detecting anything, it's not presenting you with any information, it's not cluttering any information, you have the ability to also filter defects. So if you're perhaps in a, looking at a HP turbine blade set and you're purely wanting to check for the presence of cracks, you can filter off TBC loss or oxidation, so it doesn't present bound-in boxes that correspond to those defect classifications. Only present the one, for instance, let's say you're checking for cracks. So again, you don't want to be presented with too much information on the screen or unwanted information on the screen. So there is a very useful filter function whilst you're using ADR. So it's only presenting you the bounded box, for instance, that corresponds to the classification that you're interested in. Lots more information. You've heard me say several times now about the data sheets. These are accessed on the Waygate Technologies website. And we also have this cloud forum called InspectionWorks. That's the link to InspectionWorks. Please do explore that space, inspectionworks.com. We have a store. It's basically a platform upon which we can, and you can, as customers, can deposit your information and your inspection data and share that data, report the data, and do all sorts of things with the data as a part of that InspectionWorks ecosystem that's called the store. And so we've dropped in all sorts of documentation and information that hopefully you'll find useful, part of which are these data sheets. So we've got, for each analytic, we have a data sheet. So there's four data sheets there. And you can actually access these data sheets directly on your borescope. So if you go into the analytics menu, highlight or focus the appropriate analytic, let's say you've highlighted blade counter using your joystick, or you've tapped it on the screen, by pressing the info button, a few seconds later, the data sheet appears on your screen. Admittedly, it's a small screen using, if you're on the MViQ, but it's a very clear, very seamless experience. So yeah, analytics can be also found on there, analytic data sheets. So that brings the session to a close. Now's time for questions, if we have any. Right. Thank you, everybody, for connecting and sticking through. But yeah, if there's no more questions or any questions, then I will stop the session now. Okay. Thank you again. Goodbye.